So, as I was saying, number 1D, that W that I have highlighted should be a T. So what I'm looking for is, for example, just make sure this is clear. No, we haven't talked about nonparametric resampling yet, or the nonparametric bootstrap yet, but we will later today. So, for example, do this quickly, or not. So you could have a resample that looks like this, a resample that looks like this. You could have a resample that looks like this. Okay? So obviously this first resample is different from the second and the third, right? Okay. Now, in part A, it says how many possible resamples are possible? Did I actually say that?
You really did.
Oh, gosh. I rewrote this a number of times, to be honest. How many possible resamples are there? How about that? That might sound at least a little bit better. So how many possible resamples are there? Note that these resamples are not necessarily unique. So in this particular case, these would be two different resamples. Okay? Now in part D then, how many unique resamples are there? Then the last two resamples that I have listed up here are the same. So that's the difference between part A and part B. Are there any questions about that? And I strongly urge you to take a look at Quantile Function because we'll find some good help in there about how to answer this question, these two questions, including Chapter 1 of Quantile Function. There's some stuff in there as well. Okay, so let me get back to what I was going to start with at the very beginning. So project number 1 is due Thursday, September 13th. There was also one other thing I wanted to bring up about project number 1 regarding problem number 2, and that is, and I don't think I mentioned this last time, so that's why I want to make sure I bring it up now. I'm going to do a purple pen this time. The book will often say something like this: var star s squared. This is equivalent to what we would in our class say var star s squared, let's say star. Quantile Function are not very as specific as they should be regarding what's based upon resampling. So please be careful about that. That's why I have here, for example, I let t be this s squared. I have var star t star.
So Quantile Function has var star s squared. Is that what you're saying when you say the book has?
The book has this.
Okay.
Sorry.
And that's Quantile Function book.
Okay. I guess I didn't know our book, even though this is by Davison Hinckley. I didn't know it by BMA.
Right.
I mean, as you can see, and especially as we go along further in course, that the notation can be quite tricky to make sure that you know exactly what's being talked about. So it doesn't help when other books use other notation. Life would be so much simpler if we all use exactly the same notation for everything. Anyway. Okay, we will continue in Chapter 2 today, finish up the parametric bootstrap, and start the non-parametric bootstrap. Are there any questions? Okay. So we left off on page 21. It's a good place to leave off because there happens to be kind of a review of what we've been doing. So I don't know, I guess maybe I'm repeating myself too much, but I think it's helpful to repeat sometimes. And that is, before coming into this class, your statistical world consisted of, let's say, saying a random variable y has a particular distribution called f and indexed by some parameter psi, where psi can be a vector of parameters, for example. And with this particular distribution, then we take a sample from it, and we get y1, y2 down to yn. And in this particular setting, we might be interested in, let's say, a particular parameter theta, and we're going to estimate it with a statistic t. This theta could be just one particular element of a vector psi, or it could be like a little combination of the parameters inside. It could be other stuff too. We're going to estimate it with t, and the observed value of t is going to be then some function of your data. Now we can come up with an estimate then for what f is by simply finding the estimate of psi, called psi hat, and plug it into f, simply put. And once we have this estimate of this distribution, and that's where the Bootstrap can come in, where now we have a way where we can take samples ourselves, which we call resamples. So the first resamples, y star 1, y star 2, down to y star n. I can also put an extra subscript in there to indicate what particular resample I'm talking about. And we get t star 1. So we calculate our statistic of interest now on the resample. And we get t star 1. We do for t star 2 down to t star r. And what this is going to give us then is a way that we can estimate then what g is going to be. I should say t is distributed g. And if we use capital R resamples, then g hat r allows us to get an estimate of g that way. Since this is a parametric bootstrap, often we can get g hat exactly through some mathematical derivations. Okay. Now with that as a setup, what we'd like to be able to do is use these resamples then to come up with an estimate of bias. In actual application, you're typically not going to know exactly what the bias is. The reason being is because it's dependent on a particular parameter. So let's let the bias, the true bias, be beta. And this is what you'll learn in your 883 class. Bias is the expected value of your statistic of interest given samplings done from f minus the parameter of interest. T is estimating theta. We can write this data then also as a statistical function, which is helpful then when we look at a way to estimate then the bias. So what we can do now is put hats on top of the f's. And now to avoid possible confusion about what a random variable is and what distribution it comes from, we put a star also on the t to indicate, okay, this t star comes from f hat. T comes from f, t star comes from f hat. And again, as emphasis, and you'll see me do this a number of times today, remember that the book does use different notation to mean exactly the same thing. So a little bit of a shorthand notation for this expected value would be to say expected value star of t star, and then subtract off t. And that is our bias. With a parametric setting, often you're going to be able to actually derive what this expected value is, but in some settings it might be difficult. Maybe the math is too messy. So what you're going to need to do is actually use our resamples then to estimate this quantity. And all we do is now we replace then the expected value with simply, from actually doing, let's say, capital R resamples, then the average. Now note that, because we're using the Bootstrap here, this quantity, or equivalently that one, can be actually calculated. So we have a way to know what the bias is. Well, it's an estimate, but we have a way to get at what the bias is. And without the Bootstrap here, you're not going to be able to do that. Of course, by the law of large numbers, this B sub r goes to B. S r goes to, r gets large. Okay. Often in my notes that before class, I always go over my notes before class. I just walk through what I plan to discuss. And there are times where I want to make small changes in the notes. And usually what I do is I put those changes in blue to differentiate from red that I'm using for my writing. I think it just simply would be clearer to differentiate parts of my notes by actually putting a label here called estimating the variance. So we just had a label called estimating the bias. Now we're going to talk about estimating the variance. And to emphasize what we're doing here, there is a true variance of t that's out there. This is dependent on parameters. So let's say dependent on parameters. Now the way that we often estimate this is to calculate var hat of t, where we put the statistics in place of the parameters. So for example, I often will use this because it's just an easy thing. Suppose t was the sample mean. So let's say it's y bar. If I want to find the variance of t, of course, that's sigma squared divided by n. And then the variance hat of t is then sigma hat squared divided by n, or say s squared divided by n, whatever notation you want. Now, what I like to do is come up with a way to use now the Bootstrap to estimate then this variance. And the way that we can denote that is by one way, var star t star. Okay? And since we're in a parametric Bootstrap setting, we could actually derive it. Oftentimes, though, we want to take the actual resample, so we could say var star and then a subscript r there, t star. Use r resamples to get it. Well, how would we get that then? Well, then, this is book's notation now. V subscript r indicates over r resamples. All you do is take then the old sample variance, the unbiased sample variance of your t stars. Now I wrote this purposely because there are times we're going to need to differentiate this. I wrote this purposely as a random variable. So notice the capital T's there. Now when you're actually physically taking the resamples and you actually get the resamples and calculate the actual t stars, so then we have a little VR here to note the actual observed quantity. I guess also for emphasis, let me go back up here. When I was talking about the bias, I could also define b sub r, little b sub r, to be this, just to make sure it's clear. Okay. Now we could also, so we talked about bias, we talked about variance. Well, what about quantiles from a distribution? We can also do that as well. Now, so far what we've been saying is that T is distributed G. Oftentimes, though, instead, the book, and then I will as well, say, why don't we say T minus theta is distributed G, so just a simple shift. And the reason being is because we're often going to be working with deriving confidence intervals. And, you know, in order to derive a confidence interval, if you remember, like for a confidence interval for mu, you often start off with, let's say, y bar minus mu. You end up dividing by the usual stuff. But you need that mu in there in order to do some algebra and get your confidence interval for mu itself. So that's why often we work with t minus theta versus just t itself. It'll always be clear which is which, and when we're talking about what g is. But if I want to approximate now the distribution of t minus theta, I can do that with the distribution of t star minus t. So in other words, my distribution g evaluated at some value u, which will be probability t minus theta less or equal to u given f, then is equivalently expressed as g hat of u. So again, think of this as a CDF, like probability t star minus t is less or equal to u given f hat. Derive that typically in a parametric bootstrap setting, or you could use actual resamples. And notice a little small change there. That should be a little t rather than a big T. And if using over R, capital R resamples, you know, just simply use the indicator function to look at how many times t star minus t is less or equal to this u. Okay? So that allows you then to estimate then the density, or I'm sorry, I guess the CDF evaluated a particular value of u. But let's say that you want instead the quantile of g. Well, what can we do? Well, let's define q sub alpha as the alpha quantile from g. And notice the notation I use here is the inverse of the CDF of g, evaluated alpha. So just to give you some similar notation or similar example to something you've seen before, suppose that k is a CDF that is normal, let's say standard normal. And then if I say k inverse of 0.95, that would be equivalently equal to 1.645. Just make sure that you understand that. So 1.645 is the 0.95 quantile. So what we like to be able to do here is find q sub alpha in this particular equation. Why? Well, think of all the places where we use quantiles in statistics, like for confidence intervals. So you might think, well, maybe the Bootstrap could help you basically, you replace the old t-tables with some other tables based upon the Bootstrap. And in fact, that's what we will do for one of our confidence interval methods later on. And so what we can do is then solve for q hat sub alpha in this probability expression there. Please note the little extra alpha there. That's if you have a nice little parametric expression for the distribution of t star minus t. Alternatively, what we can do is use resamples. And now what we can do is find all your t star minus t's and look at the alpha times r plus 1 ordered value from these resamples. So notice the notation here. We have a little parentheses around that subscript there. Remember how you use those kinds of parentheses to denote order statistics? So what this represents is that you find the r plus 1 times alpha order value t star, subtract off t, and that's your estimate of the alpha quantile. So for example, let's say that capital R equals 999. Then if alpha is 0.01, that says simply find the 10th smallest t star of all your resamples, subtract off t, and there you have an estimate of 0.01 quantile from g hat. So why are we using R plus 1 here rather than just simply R? It all depends upon your definition of a quantile. And guess what? There are many, many different definitions of quantiles, all differing on a small little piece of it. In fact, in the quantile function in R, there are 9 different ways to define a quantile. Our book just uses one particular one that corresponds to basically what I showed you for a QQ plot. Okay? Basically, it's the same concept. Specifically, you can think of it this way: that that the expected value of the jth order statistic is approximately, let's say, suppose I have some CDF k, and I evaluate the inverse of the CDF at j over n plus 1, where capital N is the sample size. So you can think of capital N playing the role of R, and you see that R plus 1 in there, and that's basically all where it comes from. In other Bootstrap books, they might use just simply R itself versus R plus 1. For example, Ephraim and Tim Sharani, they will use R plus 1, although they call it B instead of R, B for Bootstrap. Anyway, we will deal with R plus 1 times alpha quantile a lot throughout the rest of the semester of the course, and you're going to see that a lot coming up. Okay, so let's take a look at another example. This is the air conditioning example. And if you remember, what we have is some data of how long these airplane air conditioners last. And we have just a sample size of 12 only, so a very small sample size. And we're going to be interested in getting at the average length, average duration of how long these air conditioners last. And for our sample itself, we had 108 hours. Okay? And we saw that maybe an exponential distribution worked okay with this particular data. So if we're doing a parametric bootstrap, then we just simply say y star is distributed exponential y bar. Equivalently also, I should say, since this is a parametric setting, also we know that y bar star is distributed gamma n y bar. And this is again using the definition of the gamma distribution given in the book, not Cassell and Berger. Perhaps I go back and forth here too much here, but we could also call t equal to y bar, so then t star is equal to y bar star. What's the bias now? So if I'm using y bar to estimate the mean lifetime of these air conditioners, what's the bias? Well, what we could do is take some resamples. So it's on page 25. And calculate then basically the average of the t stars minus t. Alternatively, since we know since we have a parametric bootstrap, we know what this expected value of t star given f hat would be. Well, it's simply y bar. It's an exponential y bar. That's it. So in fact, the actual true bias happens to be 0. The true bootstrap estimate of the bias is 0. Is it getting hot in here again? Okay. Hopefully this will help. Brings me back to the first day I ever taught. I was at Kansas State University, just beginning my master's program. They immediately put us in front of the class, and I was teaching a Stat 218 class all by myself. Never had any teaching experience at all. And we got 45 students, and guess what? No air conditioning. It's in August. It was 100 degrees outside. But I kept my students there the entire class period. Anyway. Also, interestingly, there was a nuclear reactor right next to us, too. Just a little side note. They have a nuclear reactor on campus. Anyway, let's use the bootstrap then to estimate this bias using resamples real quickly. Okay, so let me get back to the right place in my program. So here's what the data looks like. Notice it's in a simple vector. And to actually do then the parametric bootstrap, I think I showed you last time how to use the boot function. You can use a boot function for parametric bootstrap. I sometimes just think it's just easier just to simply use the corresponding a function R for a particular distribution. So that's what I'm going to do here. So I'm going to set my R to be 500. You'll see why I have R.maxIf versus just calling it R. We'll see why later. Set a C so I can reproduce the result. Use the REXP function to actually take my resamples. So notice I'm taking N times R resamples. Remember how R parameterizes the exponential distribution. It actually does 1 over, let's say, mu. So, which is different from our book and also Quantile Function. So that's why I have 1 over T, in other words, Y bar. Number of rows R, number of columns N. I put this all in here. And there's my first resample. So here is Y11 star, Y12 star, and so on. I use then the apply function, which we've seen before, to my resample data. I'm going to use the mean function that's applied to every row. And here are my T star. So T1 star is 70.97. And lastly, let's estimate then the bias using these 500 resamples. I get negative 1.26. Well, close to 0. You might be thinking, geez, that's not that close. Well, you have to put it in the context of the size of our observations. I mean, we have some observations that go up to 487. So yeah, that is close. Okay. Any questions? It's not too difficult. Let's now talk about estimating the variance. The true variance, again, putting to the parameterization of our gamma distribution for a book. Our true variance ends up being Y bar star divided by N. Please make sure you verify that on your own. And you get 973.5. If I were to take resamples then, as we just did, I get 812. And again, you might be thinking, because that's kind of far apart, but remember also the scale that we're working with here. We have squared values for, squared units, you could say, for our variance. So, you know, if you took the square root, so if I take the square root of 812, and if I take the square root of, what is it, 973, you can see that they're a lot closer than what we had thought maybe perhaps before. But of course, you know, it makes you wonder, well, what would happen if you actually did take a larger R? You know, we're using R of 500 here. Is that enough for the law of large numbers to kick in? Yeah. I took 10,000 samples, and I did end up getting a little bit closer, which you would basically expect. So using 10,000 resamples, look at my bias, it's getting closer to 0, and also look at my variance getting closer to what the actual true variance is. So just to emphasize my point here in terms of the notation that I used earlier. So again, this would be var star t star, and this would be var star t star, and then subscript r equal 500, let's say. So here, you know, now you can think of that, you know, pretty much any problem out there, you have a way to estimate a bias and how to estimate a variance now. And really, you know, you don't need to mathematically derive anything. You just be able to simply implement it in R. Okay. So the purpose of this next part is to actually reproduce figure 2.1. So if you could take out your book, let's talk about figure 2.1. And what we see, this is on page 17, sorry. What we see here is, well, kind of a way to visualize how large R should I take. And what you would expect is that as R increases, the bias is going to put in a non-statistical term, calm down in terms of its variability is going to get smaller, 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 and go to where it should be. And so the plot begins with, well, what if I took R equal 10? What if I took R equal 20? Then R equal 50? And you can see that eventually, once you get to about 500, it seems like things are getting closer and closer and closer. And you're starting to get a more reasonable estimate for what the bias would be. And sorry if I didn't say this before, but basically what they did was they took 4 different runs of this simulation. So you have one line that represents, let's say, the first time that I took 10 resamples, 20 resamples, 50 resamples, and so on. The next line represents, well, 10, 20, 50, and so on. And what I like to do is be able to actually reproduce their plot. I'm going to go through the details here this time because it's going to be helpful to do stuff later on in the course. So let's begin with this. R max is going to be 500 because I'm going to look at most of 500 resamples. The actual R values I'm going to look at corresponding to the book are 10, 20, 50, up to 500. I'm going to save all my results eventually in a data.frame. And I'm just simply going to initialize it with R.values, bias, I'm going to calculate for every R, variance for every R, and the simulation run, 1, 2, 3, or 4. So I'm going to just initialize these with nulls for now. Set a seed so I can reproduce my results. Create vectors to save the bias and variances that I'm going to calculate for every single value of R. So, just to show you, some of you, for example, in the day number 1 quiz would actually, let's say, use the function matrix to save results and to initialize some results, and then eventually, use the function matrix to save results in, where you would first initialize it with maybe zeros or null value and so on. When you only have, let's say, one thing that you're computing every single time, often it's just simpler just to use the function called numeric rather than matrix. And what this does, it creates a vector that's initialized with zeros. So it has a length of R values corresponding to, I'm going to put the bias in there for R equal 10, 20, 50, and so on. There are other ways that you could have done this little, I guess you could say, simulation here. I just chose to do it this particular way. And I'm going to use a for loop to allow myself to replicate this result 4 different times. Each time I find my Y stars, I find my T stars. I'm going to create a counter. And then another for loop that allows me for every single R value, 10, 20, 50, 100, and so on, I'm going to do the following. Find the mean of the T stars for resamples 1 up to resample I. So the first time through this loop, it's going to be 10. Next time it's going to be 20. Next time it's going to be 50, and so on. Subtract off T. Put that into bias, the first position of bias. Do the same thing for variance. Reinitialize my counter. Come back up here. Get the second value of R. Put the results in the second element of bias, and so on. Then I put all my results, the actual R values, the bias, the variance, and simulation number into something I just call save. And then, simply, I'm going to take what was in save and put it down below what's in save 2. Let's take a look at what's in save 2. Remember, that right there was initialized. So the first time through, it's basically I'm going to say, here's save 2. I'm going to put save right below it. And you're going to have the results from simulation 1. Then the next time through, it's going to put the next save right below, and so on. let's run it through here first, and then I'll go back and help explain some of this stuff a little bit better too. Okay, so let's take a look at save 2. So the first simulation run produced these values of bias and variance for the corresponding values of R. The second simulation run produced these. Now, if you're ever confused about, what's happening here in this loop, what's happening in save and sub, don't forget that you can put some other stuff in here to help you remember what's going on. So if I put maybe print save, maybe I put print bias, print I, do I first. And let's just do one simulation run just to demonstrate this. Okay, look what happened. So the first time through that inner loop, when I was 10, here's my bias vector. Second time through that inner loop, I is 20, meaning R is 20. And look at my bias being put in there. Then we'll do one more. I equals 50. Here's my bias, and so on. So that eventually down here, so this would be my final save. And then save gets put into this save 2. Something I failed to mention before, if you haven't seen this function, it's called rbind.data.frame. rbind stands for row bind, meaning combined by rows. So if I have simply 2 data sets and they're the same structure in terms of the same variables, if I say rbind set1, comma set2, I'm going to put set1 here, I'm going to put set2 right below it. Sorry if that wasn't clear. Okay, so there, let me rerun this now with 4, so I get my results that I need. Okay, so let's look at save 2 again. What I need to do is graph this. I want to reproduce that figure that we saw in the book. So what I'm going to do is just show you first what the bias graph looks like. I'm going to print the R values on the x-axis. I'm going to print the bias values on the R values on the x-axis, the bias values on the y-axis, and produce the plot that's on page 228. So to do that, I'm going to use the plot function. Here are my x-axis values, y-axis values. And then what I need to do is tell R, do these values correspond to simulation run 1, 2, 3, or 4? And the way that I do that is by specifying particular colors and plotting characters for the items that are being plotted. So let me just highlight this so you can see what happens here, then I'll explain it. So in the data frame save 2, notice how the first 8 correspond to simulation 1. So I want all those to have exactly the same color, all those have exactly the same plotting point. So when I say REP, that stands for repeat, I want to repeat the colors red, blue, dark green, and light blue times equal 1, but each of the colors are going to be repeated corresponding to the number of R values. In other words, there are, just said before, 8. So what happens is I have 8 reds, 8 blues, 8 dark greens, 8 light blues. Same thing happens then for the plotting characters as well. So that then I just simply, I'm also going to put a horizontal line at 0, and I get this plot here, which shows you what happens to the bias for each simulation run. And it would be nice if I could join these points with a line to help you see better what's going on. How do I do that? Use the lines function. So I specify my x-axis values, my y-axis values, and the corresponding color to print. The first lines function corresponds to simulation number 1. So look how I pull out of save2 and $bias. Those are all my biases. Look how I pull out only those corresponding simulation 1. I say save2 $sim equal 1. So you want to know what happens with that. It's a logical test. So I'm going to get a bunch of trues and falses. The first 8 will be true because that corresponds to simulation 1. Okay? So if I just execute this code, look at the plot, you can see all the simulation 1s are joined. And let me just keep on going here. I'm going to put a nice little legend on the plot too. And there you go. So you can see, as this is again trying to reproduce that figure in the book, we can see how the bias, is going to where it should be. On your own, take a look at how I did the variance in a very similar manner. So, how large of an R is necessary? Well, maybe R equals 300 would have been enough. Obviously, 500 does pretty good too. But another way to kind of answer that question is to look on page 228, at the very bottom. And we can derive some of the stuff mathematically. So what is the variance star of the bias, this bias estimate? Well, let's go through this. So if I were to take then the average of the t stars, subtract off t, that's my bias. What happens when you take the variance of a constant? It's 0. Well, in terms of the distribution for f hat, t is a constant, right? So look what happens. That t part disappears, and I just have that summation in there, and I brought out this r outside, so that's why you see an r squared there. Then I can find, well, what's the variance of t star itself? Well, what's t star? What's the average of the y's? Y stars, I should say. So I can, again, bring this n outside. This is squared. I can move the summation through. The reason why I can move the summation through without worrying about the covariances is because of what? Independence of the y stars. To remember how we're actually taking the resamples. It's a minor, kind of a minor point there, but obviously it's important. And that's why, again, we're resampling with replacement. So what's the variance star of the y stars? Well, using the definition of an exponential, for our case, simply t star. So then the variance var star of b sub r is t star divided by n times r. So you can see the role that r has in estimating, in terms of the variability of those bias estimates that we were seeing over those 4 simulation runs. And then obviously as r increases, well, that's going to decrease then this variance that you see in that plot. Okay. Are there any questions? Well, what about quantile estimation then in this particular setting? I'm not going to go through this in as much detail as the previous example because a lot of the ideas are similar to what we've seen before. But let's say that I want to, get at then the r plus 1 times alpha quantile from t star. That will allow me then to estimate a particular quantile from g hat. Okay. Now, first though, and this is again reproducing some stuff that's in the book. First though, remember what t is. It's a simple sample mean. And we know from the central limit theorem that the sample mean has a normal distribution for a large sample. N is equal to 12 here. What do you think? Might not work out well. So let's look at what would happen if I just simply looked at a normal distribution to approximate then these quantiles. So what I'm going to do is take my resamples. I'm going to use 999 resamples here. Find y star and t star the same way as before. Find a QQ plot for using, let's say, just 99 resamples, just to see what it looked like. And also use a QQ plot for r equal 999 resamples. The QQ plot's very similar to what I've done in the past. So I'm not going to go through all the code behind it. But do note that when I find these quantiles, when I use a normal approximation, that normal approximation simply uses the mean of all the t stars and the standard deviation of all the t stars. So here are my QQ plots. Let's just focus on r equal 99. So if you saw that, what do you think of normality? It's not too bad, except for right here. Again, to judge a normal distribution with a sample size of 99 can be kind of tricky at times. But look what happens if I have 999. Now you see where that deviation occurs in the tails. And you see more deviation in the right tail. Why do you think that happens? It's the actual distribution for t star. Gamma. Right skewed. Yeah, that's why. Okay, so, well, let's actually now do a QQ plot again, but now using then the correct gamma distribution. Please, on your own, make sure that you understand this aspect, and that is our gamma distribution in Cassel-Berger's notation, R's parameterization would be alpha equal n, beta equal t divided by n. In our notation for our book, though, instead, t star is distributed gamma and t. Be very careful. Trust me, I've gotten confused a number of times before. So I do the same kind of plot using quantiles for a gamma instead. This is what I get. What do you think for r equal 99? So I'm using the first 99 resamples here. Yeah, I might be a little worried here, but again, that shows you, you got to be careful with these QQ plots. This should work out. Remember? So we know what the distribution is. These t stars should have a gamma distribution. Well, then look what happens then for r equal 999. Now things settle down. And the QQ plot does what we would expect it to do. And again, you see a little deviation in the right tail, but remember, that's to be expected because we have a right skewed distribution. It's hard to estimate those far out quantiles for a skewed distribution. You should think of it this way. This would be the 0.001 quantile. Well, if it's right skewed, you might not get it exactly. Okay. You could also look at histograms as well. We've looked at histograms before with particular distributional overlays, so I'm not going to go through all the details here. The first set and this is just reproducing stuff that's in the book, are for the normal distributions. So I plot a normal distribution over a histogram. Maybe it doesn't look as bad as maybe some of the QQ plots did, but that's because histograms can kind of distort things to some respect because of the class widths. But we do see some deviations from the normal distribution. I think we can all agree on that. And I guess for some reason I did not do the corresponding plot with a gamma distribution. But what I did do is I actually looked at the numerical quantiles. So the particular quantiles I'm interested in, I'm going to put in a vector called P, 0.01, 0.05, all the way up to 0.99. And for each of these quantiles, I'm going to use the distribution of T star from the resamples, I use the quantile function. I think we've seen the quantile function before, haven't we? Maybe not. There's a function called quantile. And it allows me to find the observed quantiles. So I say t dot star, that's what I'm interested in finding the observed quantiles from. The probs argument allows me to find 0.01 to 0.05 quantile. And then the key thing that we always need to specify where we use the quantile functions, we will use that a lot in this class, is type equal 1. Remember how I said there are 9 different definitions of a quantile? Take a look at the help for R. You can see all 9. We will always use type equal 1, because that corresponds to what the book does. So this will actually find then the correct ordered value. And then I'm going to compare that with quantile from a gamma function, again making the necessary adjustment from the book's notation to R's syntax. And here are the corresponding quantiles, and as you can see, they largely agree, which is what we saw in the QQ plot. Just to emphasize my point here, let me show you how I actually found I can find some of these ordered values. Make sure I'm in the right spot in my program, sorry. Okay, that's what I did. So I'm going to do a head T star here, n equal 20. And this is going to give me my first 20 different T stars. Let me actually do a sort on that as well. So here's my sorted T stars. Now, if I want to find the 0.01 quantile using our book's definition, what that says is I need to take 999 plus 1 times 0.01. I need the 10th location. So I do sort T dot star again, and then I'm going to do brackets to allow me to pull out 46.55, the 10th ordered value, which is right there. And that matches up what we have on page 233 for the very first T star that you see in that data frame. And that, in the notes, that was calculated using the quantile function. Okay. So it's just a good exercise to get familiar with the parametric bootstrap, what you can do with it to compare a normal approximation, which is what you might have used otherwise before using the bootstrap. Just some nice comparisons there. And I think that takes us then real quickly to one last thing with the parametric bootstrap before we get to the non-parametric. If you by chance still have that Chapter 2 extra handout, you can take that out. We're just going to talk about it for a minute. And I want to show similar calculations with this particular example. If you remember, this dealt with wind speed using the Rayleigh distribution. So this February wind speeds in Lincoln, Nebraska have an approximate Rayleigh distribution. And in this particular case, this is what the Rayleigh distribution looks like. And we were interested in calculating the maximum likelihood estimate for beta, called beta hat. And we simply denoted this by T. And we looked at how one could take resamples and stuff. And is that thunder?
Yeah.
Wow. Wasn't expecting it. One area of statistics where there's probably a lot of work that can be done is weather forecasting. I know I get frustrated at times when I watch the weather at night and say, oh yeah, it's going to be a nice day, and then, what do you know, it's sweet. Especially when they say the high temperature is going to be 90 degrees. Well, I want to
Plus
tell
or
the
minus 2.
yeah, I want to know the confidence interval for that. Okay. Actually, when I was in grad school, I actually emailed the local ABC webcaster. I said, "Do you ever do that?" And he didn't bother getting back. But supposedly, I guess weather forecasting, like in the 1990s, was very deterministic, where they wouldn't bother with that kind of stuff. And now what they're often doing, I'm not an expert in just stuff I've seen at like the joint statistical meetings, is that often they come up with what's called an ensemble of models. They have a whole bunch of different models that have various starting conditions that are very dependent upon where the models, I guess you could say, start from. And so they run all these models, and then they measure the variability based on what these models show in all the detail. So let's look at now. I have all these t stars. I'm not going to go through all the resampling how I did before. If I find a var t star, you get 0.1088. I can also do the estimate of the bias as well. So now you know how good that estimate of the MLE, how good that maximum likelihood estimator is. Now, if we compare this to what the asymptotic approximation would be, I'll let you look at that on your own, what the asymptotic distribution was. One could look at the variance, and I get 0.109. Look how close they are. So the bootstrap and asymptotics are green, which is nice. I mean, we have a fairly large sample size, and so you hope that happens. What's the bias in the asymptotic setting? What would we say the bias would be? Maximum likelihood estimators are asymptotically unbiased, so 0. Look at that. It's about the same. So again, just to confirm results that you may have seen elsewhere, how things come about with respect to the bootstrap and how you get similar results. Okay, finally, let's get to the nonparametric bootstrap. So we will do the nonparametric bootstrap more often. But there are problems where we'll do the nonparametric bootstrap more often. But there are problems where the parametric bootstrap comes in handy, and plus it's also it's a useful learning tool for how to work with the bootstrap. Okay. So now f hat is the EDF. And that's what we're going to take our resamples from. If you remember, what that basically means is every single value in your original sample has a probability of 1 over n. And we resample with replacement. Now, there are actually a finite number of resamples. And as you will see in the project, the total number of possible resamples that are unique are 2 to the n minus 1, choose n minus 1. You can plug in some values of n on your own. You can see how quickly that just gets very, very, very big. In fact, as part of the project, you are actually finding all possible resamples a few times. I think in problem 1, the sample size is 4, and so it's manageable still. I think some people were saying it was 35. I won't confirm if that is correct or not, but it's a manageable number. But then, once we get to problem number 3, I ask you to find all possible unique resamples again, and I think there's a sample size of 12 on that, and now you start having problems. In fact, R is going to say, you can't do it. So you can see how that finding all possible resamples is difficult. I mean, if we could, that's how we actually would proceed with the bootstrap. Always find all possible resamples. Instead, what we do is we appeal to the law of large numbers by taking, let's say, a large number of resamples, like 1,000 or whatever, and use those to approximate what would happen with all of these. Okay. So let's talk about how we can do some moment estimates here. And actually, there are some estimates that you can actually derive by hand, and that's what we're going to do here. And that helps you see what the bootstrap is going to be doing in a more complicated setting. So again, let's say that y star is distributed f hat. And I'm going to be interested in finding, for example, the expected value of y star. Let's go back to set 882. And how would you find an expected value? You know, the actual full description when you have a discrete distribution. So let's say x is my random variable. I want some function of that x. We're just going to call it g of x. I want to find the expected value of that. Well, what you would do is take the sum over all possible values of x in your sample space. That's what that script x represents. You would take g of x then times the probability that random variable x is equal to one of those possible values of x. If there are n different x of j's possible, then you can simplify the notation by saying sum j equal 1 to n of g of xj times the probability x is equal to x of j. Let's apply this now in a Bootstrap setting. So what I want is expected value of y star given f hat, or equivalently expected value star of y star. So I'm going to take the sum over all possible values that y star can take on in my sample space. You should think about what will be the sample space in this case of y star times that corresponding probability. Or equivalently, we know there's n possible values of y star, so we could take the sum over all those possible values, j equal 1 n. And then what's interesting is this. We also know that these y stars can only be equal to y1, y2, down to yn. So we're resampling with replacement from a fixed set of values. So I can drop off the stars on these little lines. What's this probability then? 1 over n, and thus you get y bar. So in a nonparametric Bootstrap setting, expected value of y star given f hat is y bar, which makes sense. Because again, we're resampling from f hat. And what would you expect on average a y star to be when you're resampling from f hat? Well, the average value. What about the variance? So it's var of y star given f hat, or equivalently var star of y star. Let's go through the same thing as what we just got done doing. It will be the sum over all y stars in your sample space, y star minus expected value star of y star, which is y bar, squared times the probability. Go through similar details. And you get this. 1 over n times the sum yj minus y bar squared. Or if you want to, you can go a little step further, compare it to what s squared is. N minus 1 over n times s squared. So you can see you get very, very close to the actual sample, the usual unbiased sample variance. Let's look at some other moments. How about y bar star? Well, again, go through the details there, and you get y bar. So that's good. And again, think of this in terms of what you learned in your first stat class. When you first saw the proof of the expected value of y bar is equal to mu, the population mean was mu. Well, essentially, we're saying now the population mean, and be careful with that, population mean is y bar for this sampling process. And in a similar manner, var star of y bar star is then, let's see, 1 over n times that variance that we had before. Compare that to, variance of y bar is sigma squared divided by n. The variance hat of y bar is, you could say, s squared divided by n. So you can see you get something very similar to this other more common estimator that you're used to seeing. Now, will these little small differences really matter if you have a large n? Yes. Okay, that takes us to page 41. So what I've just shown you are the exact expected values and variances from the nonparametric bootstrap for specific quantities. Again, in actual application, you're not going to have as simple of statistics to work with it, to actually find it, generally speaking. So what you would often do is just simply take resamples, use the law of large numbers, and calculate expected values as 1 over r times the sum of the t stars. To find variances, similar to what we did with the parametric bootstrap, use that formula there. Okay. Let's talk about taking these resamples. There's 3 notes here on page 41 and 42. I'm going to do the second note first. It's on 42. There's an interesting relationship between the nonparametric bootstrap and the multinomial distribution. So if my original data was y1, y2, down to yn, essentially what this means is I have n different categories, right? And what do we use a multinomial distribution for? Well, when we are sampling in a setting where you have n different categories, let's say. And what's the probability of each category here then? 1 over n. So resampling with replacement is equivalent to sampling from a multinomial distribution, where the probability of being in a particular category is always 1 over n. This is very useful in various theoretical derivations. Now, there's another way that you can think about how this resampling takes place, and this is very useful because this is what the boot function does for nonparametric resampling. And that is, forget the fact that you have this little y symbol here. What you're basically doing is sampling. Let's go a long walk out to my car.
It's not going to last very long.
Anyway, so you have you're resampling. What you're doing is actually sampling indices. Index 1, index 2, index n. Maybe you might get index 3 2 times. Maybe you might get index n 1 time. Maybe you get index n minus 1 0 times, and so on. So what you could do is, let's say that we had a simple, suppose we have a sample size of 3, just to make things easy. And let's say in my resample, y1 star is y2, y2 star is y2, and y3 star is y1. Now, basically what this is saying is that you want 2 of the 2 indexes and 1 of the 1 index. Sorry, I picked those numbers. In an R context, suppose your data is in Y. Then all you need to do is this. Put those indexes, combine them together in Y, basically. And then it allows Y to pull out Y2, Y2, Y1. And that's how the boot function works. It actually resamples the indices, or maybe I should say samples the indices, rather than physically actually sampling the Ys. Okay. Lastly here, the book has an excellent example of the nonparametric bootstrap. Make sure you read it. To help you out, I've actually reproduced some of their stuff in my example 2.8.R program that I'm not going to talk about in class. But if you have questions, of course, you can ask about. But what's interesting in their example is that they use their interest in the following statistic. T is equal to x bar over u bar. So they have some data they call x, they have some data they call u, and they're looking at the ratio of the 2 means. What's the distribution? Well, what distribution would you use outside this class? I don't know. It's a ratio of 2 means. not an easy, necessary distribution to work with. And what they show is how, in a very simple sense, how to work with a non-parametric bootstrap with this, and how, compared to the normal distribution, there is a normal distribution approximation that exists, compared to that, how the bootstrap does a better job. Okay? Well, I had anticipated getting into this example, but I think it would be best to actually end it here. So sorry about that. Are there questions? Okay, that's it for today.